Okay, we're going to go ahead and start up today's ROCKE 3D seminar. Today we have Kaushal Gianchandani from MIT, who we're doing some work with on deep ocean modeling. But today he's going to tell us all about revisiting the hard versus soft snowball debate. So if you could share your screen,
Yeah,
Kaushal will be all ready to go.
the people on Zoom see my screen.
Perfect.
They can give a thumbs up.
It's good.
Okay, awesome. Does this minimize by itself?
You might have to tell it to minimize. If you go to more, I think there's a way to hide video. That's it. Hide video. Oh yeah, that's it. Sorry, it's floating.
Shall we begin?
Yeah, please.
Thank you so much for having me. My name is Kaushal. As Mike told you, I'm from MIT. I've been working with the ROCKE 3D group, but this project that I'm going to present was the first chapter of my PhD thesis, which my PhD was based out of the Hebrew University of Jerusalem in Israel, which is where I carried this work out.
There we go.
Oh, there we go. So, as a few members of the audience might be aware, the Earth exhibited extreme glaciation events, which are known as the snowball Earth events, at least twice during the Neoproterozoic era. For those of you who do not remember these Latin names, like me, this was between 100 million years and 541 million years ago. To be precise, the initiation of the two Neoproterozoic snowball Earth events has been dated to around 720 million years ago and 650 million years ago. These extreme events lasted for tens of millions of years, which is a long period, even if you consider the Earth's geologic timescales. And as the name suggests, the word snowball Earth means that the Earth looked like a ball of snow. That's a oversimplification, but it's a good enough definition. Based on the extent of the ice cover, the snowball Earth hypothesis can be bifurcated into two parts: the hard snowball hypothesis or the soft snowball hypothesis. The image on the left-hand side of your screen is that of a hard snowball as it would be visualized by an artificial intelligence engine. These are not accurate images. But as you can tell, just by looking at the image on your left, that in a hard snowball scenario, the entirety or almost the entirety of the Earth's surface would be covered with ice, especially the oceans. Whereas on the other hand, in a soft snowball, which is depicted on the right-hand side of your screen, the Earth would be covered in ice for the most part, but we expect to have a narrow band of ice-free region near the equator. But we do not know what it was. The meridional extent of ice cover during the Neoproterozoic snowball Earth events is an open question, even though the hypothesis was first proposed in 1992. So this is going to be the focus of my talk. At the heart of this hard versus soft snowball Earth debate lie these very interesting striated rocks called banded iron formations. For the subsequent part of this talk, I would only be addressing them as BIFs because banded iron formations is a mouthful to say over and over again. These interesting rocks have been found on all of the continents as we know of today. The figure that you see on your screen right now shows the glacial deposits that have been dated to the Tertiary. And of these glacial deposits, the red ones are the ones which are the iron formations. If you put these iron formations back on the paleocontinent as it was during the Neoproterozoic, you would see that a lot of them, 5 out of the 10 on this particular arrangement, are concentrated near a hydrothermal vent. This small fact is going to be key to this talk. Again, on your screen, the red markers show the iron formations and the blue markers show the other glacier marine deposits. So the precipitation of these BIFs requires a buildup of iron in a sulfide-deprived anoxic ocean. And the ocean needs to be sulfide-deprived because otherwise iron would just react with sulfide to produce pyrite, I think it is called. So let's now talk about the hard versus soft snowball debate in light of the banded iron formations. As I had mentioned when I began this talk, that a hard snowball signifies a snowball Earth state in which the entirety of the Earth's surface is covered with ice. So in that case, there would be very little to negligible air-sea fluxes. This would render the underlying ocean anoxic, and that would allow for iron 2 to build up in the ocean. To put things in perspective, iron 2 is not found at all in the present day ocean if you're considering a global scale. You can find iron 2 traces near hydrothermal vents, which are sort of an anoxic environment, but otherwise all of the iron in the, a majority of the iron that is present in the present day ocean is iron 3, which is due to the fact that iron 2 is very reactive to oxygen, and any iron 2 that would come up in an oxygenated ocean would immediately be precipitated as iron 3. So a hard snowball, even though it explains the buildup of iron in an anoxic ocean, it is a strict constraint on the survival of photosynthesis-based marine life forms. And since we are having this conversation, we know that photosynthesis-based life forms did survive this snowball Earth glaciations. I could go to the soft snowball scenario and say that, okay, the ice belt, the ice-free belt near the equator would sort of serve as a tropical haven for cyanobacteria. But wherever there is cyanobacteria, photosynthetic activity would lead to production of oxygen. And we know that iron 2 has a very short residence time in an oxygenated environment. So there's an apparent contradiction here between the hard between the hard and the soft snowball scenarios. The hard snowball and banded iron formation are often regarded as an evidence to support the hard snowball. So the question, please.
Yeah. But just as to the timing of the banded iron formations, I thought that the majority of the ones that we know about were formed about 2.5 billion years ago that are associated with the Great Oxidation Event.
That's absolutely correct. But the Neoproterozoic banded iron formations are special because these Neoproterozoic snowball Earth events mark the reappearance of the banded iron formation in the stratigraphic record after being absent for over 1 billion years. So you are correct that majority of the iron deposits are from 2 billion years to before 2 billion years, but during these 2 snowball Earth events, banded iron formation reappeared in the stratigraphic record. Please feel free to chime in with questions at any point of time in this talk. So the question we are asking is, can banded iron formations be produced in a soft snowball state? There has been a lot of work regarding the circulation of the ocean in a completely ice-covered setting. However, the biogeochemistry of the ocean in an ice-covered setup has not been explored in great depth. So the goal for my PhD was to design a biogeochemical submodel that is tailored to the Neoproterozoic era and implement it in a state-of-the-art ocean GCM, which is MIT GCM. Once I did that, I carried out near global oceans.
All right, Ron, can you mute, please? Okay, keep on going.
Okay, so no problem. Once I designed this biogeochemical model and implemented it on MIT GCM, I carried out near global ocean simulations, which have a representation of sea glaciers. These are thick blocks of ice, order hundreds of meters thick, and of course, Neoproterozoic biogeochemistry. Let's look at the model configuration. So let's start from the bottom. So this is a flat bathymetry ocean. The hydrothermal vents that you see protruding out of the seafloor are merely illustrative. This ocean is heated from below. There's a geothermal flux of 0.1 watts per meter squared. The depth of the ocean is chosen to be 3,000 meters, and the thickness of the prescribed sea glaciers is varied from 200 meters to 500 meters based on the extent of the ice-free region. Meaning, when the ice-free region is wide, we expect the sea glaciers to be thinner, but when the ice-free ocean is narrow, we expect the sea glaciers to be thicker. The open ocean region in the model is forced by winds at the surface. We do not consider the effect of winds over the sea glaciers because these tend to move under their own weight, and wind has little effect on the motion of these glaciers. And since there's a prescribed temperature at Z equal to 0 level in the model, there's some melting under the sea glaciers, and to keep the mean salinity of the ocean constant, we send it out as evaporation. So the melting below the ice and the evaporation from the open ocean are in balance with one another. By modern standards, this would be regarded as a coarse resolution model because the resolution is 3 degrees in latitude and longitude, and there are 37 vertical levels. But nevertheless, the science is solid. This is a figure illustrating all. Please go ahead.
I'm sorry for interrupting with so many questions, but what exactly do you mean by a sea glacier? Wouldn't they be land-based and just have extensive ice shelves as opposed to a very thick layer of sea ice?
There would be some land-based glaciers as well, but because the temperature was so cold, the compacting of the snow over the ice, over the water could in itself turn into a block of ice. That's what I mean by sea glaciers.
Oh, wouldn't that just be a very thick layer of sea ice?
No, it wouldn't be. So if you did some estimates based on the predicted surface temperature profiles, the thickness of these sea glaciers comes out to be north of 100 meters. And in a hard snowball scenario, the model thickness comes out to be close to 1 kilometer. So you cannot treat them as sea ice because sea ice is too thin.
Well, modern sea ice that we are familiar with, but I mean, these things are floating. Is that the point? These sea glaciers?
Yes, these sea glaciers are floating, but they would also there is some equatorial landmass, so you could have some grounding on the continents as well.
Oh.
This is not a aquaplanet setup. It is a setup which has land in it.
It is good. Do they drift because of the wind?
No, they don't. They move under the pressure gradients due to their own weight. This is
So they're in the water, they're moving, they can move by.
sorry,
They can move by their own weight within the water.
Yeah.
Okay.
But a large part of them would be over the water as well.
But that's not, that's stress of the wind.
So the wind stress has negligible effect on the dynamics of sea glaciers, to put it as succinctly as possible.
Okay.
So these temperature forcings, these have been generated based on data which already existed from coupled atmosphere ocean cryosphere simulations that had been done before we did this study. So are the wind stresses. To understand our results better, we also carried out an ice-free ocean simulation. And in that case, we prescribed a evaporation or a precipitation profile. But in the ice-covered cases, you do not see an E minus P profile because I told you the evaporation is simply balancing for whatever melting is happening under the ice. So let's look at the biogeochemistry, which is the most important part of this project. Turns out you don't need much to model the present day ocean, at least the gross features of the biogeochemistry of the present day ocean. If you have some sort of nutrient, which is phosphate in this case, cyanobacteria consume that nutrient, and in the presence of sunlight, they produce oxygen and organic matter. This organic matter is used up by aerobic bacteria to give out phosphate back into the ocean. Turns out that this is all you need to replicate the broad strokes of the distribution of the biogeochemical variables in the present day ocean. Although this is a very simple model to represent the present day ocean, it is very informative because we have a lot of control over the model and we can vary the different parameters. I have not considered any inflow of nutrients into the ocean, nor have I considered a burial of nutrients of organic matter. So the concentration of phosphate in the model remains constant, and it is a prescribed quantity. Now, what if you extend the extent of the sea glacier in this model? What you would expect is that some part of the ocean would be anoxic because you've reduced the area in which cyanobacterial activity is happening. And in that anoxic part, iron 2 can build up. Wherever there is iron 2, you need to consider the dynamics of iron. So this iron 2 can be taken up by iron. Please go on. Oh, okay. I thought there was a question. Sorry about that. This iron 2, whenever it comes out in the anoxic region, can be taken up by iron oxidizing bacteria, which also consume oxygen, to produce insoluble iron 3 oxides. These insoluble iron 3 oxides, as they trickle down the ocean, can be used up by anaerobic bacteria to restore some of the phosphate and iron 2 back into the ocean. And whatever is the balance between the oxidation and replenishment settles as iron deposits. Why have I considered iron oxidizing bacteria here? The answer to that is that iron oxidizing bacteria in laboratory environments have been shown to sustain an iron deposition rate which can be as high as 20 times of abiotic iron oxidation. So these organisms may have been critical during the Neoproterozoic era. This simplified model of Neoproterozoic biogeochemistry is in balance with the atmosphere as well. And for the sake of simplicity, the atmosphere that is there in my model is only a box atmosphere. There's no dynamic component to it. The box only accounts for the number of moles of oxygen that are there in the box. So whatever steady state we achieve, the net flux of oxygen in the surface is 0 when you average it over the entire domain. So in this model, which occupies all of the screen space right now, there are only 2 free parameters. One is the extent of the marine ice that I'm prescribing in the model, and the other is the mean concentration of seawater phosphate that I'm prescribing in the model. And what we do in this study is to look at the effect of the variation in the extent of marine ice cover and phosphate on the iron deposition rate. The idea is to find configurations of phosphate and extent of marine ice for which the iron deposition rates may have been high enough to support the existence of Sturtian BIFs. We digress a little from the modeling aspect of this project and try to estimate the iron deposition rate from Sturtian BIFs, because it is important to put constraint on these numbers before we start comparing model results to any of the deposits that we have seen. So on your screen right now, you see a stratigraphic cross-section of one of the geologic formations. And you see in this geologic formation, there's some ironstone here between 20 meters to 30 meters and between 50 meters to 60 meters. To estimate the rate of iron deposition, you first need to know what is the thickness of these layered ironstones. Once you have the aggregate thickness of the layered ironstones, you need to determine what the duration of the deposition was. And to determine the duration of the deposition, we find a formation which is right below and right above these ironstones and try to estimate the age of the deposition based on the difference between the ages of these two formations. The underlying assumption here that the underlying assumption here is that iron deposition is the slowest process which happens while this stratigraphic formation is being deposited. Once you know the age as well, you need the fractional concentration of hematite and the density in these samples. I only focus on hematite because that's the dominant form of iron oxide in that in Neoproterozoic banded iron formations. You also have magnetite and some siderite. Hematite is Fe2O3, magnetite is Fe3O4, and siderite is FeCO3 for anybody who doesn't remember these.
So good type,
Sorry,
you're not good type.
I don't follow.
Good night.
Good type.
No, these, if I remember correctly, these three are the dominant iron oxides during this period. There could be trace amounts of it, but hematite is the biggest one.
Good type changes during diagenesis.
I have not accounted for any geologic processes that are happening after the iron 3 has been deposited. I should have mentioned that before beginning the talk. All right, so once you have these four quantities, you can estimate the rate of iron 3 depositions. While the stratigraphic section that I've shown to you is very clean, and you'd think that I would get a very constrained rate of iron 3 deposition during this period, that is not the case. The rate that I've obtained can vary between 0.003 to 0.4 moles per meter squared per year. The largest uncertainty comes from the deposition timescale, because it is not always easy to find a stratigraphic section in which you have constrained the formation above and below the ironstone very accurately. Nevertheless, this is the best we can do, so we work with that. Okay, now recap of our strategy. Our goal is to find combinations of marine sea ice extent and concentration of nutrients in the ocean, for which the iron deposition rates may fall under the iron deposition rates that we have calculated from Sturtian BIFs. We will try to understand the results better just by focusing on one single case. In this case, the extent of ice-free region is between 12 south and 12 north. The amount of nutrients in the ocean is 3% of modern value. And the paleogeography is an approximate reconstruction of what the paleogeography looked like during the Sturtian basin. Sorry, during the Sturtian glaciation. This paleogeography is emerging from the breakup of the supercontinent Rodinia, and we suspect that there is a hydrothermal vent here. Similarly, another hydrothermal vent is suspected to be somewhere in this region of the ocean. The stars that you see are the Sturtian BIFs that have been put back on the continents as they were during the Sturtian era. The Sturtian glaciation, not the era, Neoproterozoic era. Okay, so now we will look at the model results at two cross sections. One would be a latitude longitude cross section at a depth of 2.5 kilometers, and another would be a latitude depth cross section at 166 degrees longitude. So if we look at the latitude depth cross section at 2.5 kilometers depth in the ocean, we see that in this region, there is barely any penetration of oxygen. First of all, let's look at the oxygen concentration. This is 2 times 10 to the power minus 6, which is, if I remember correctly, 2 orders of magnitude lower than the lowest concentration of oxygen that is there in the present-day ocean. It is the present-day ocean, the minimum is 200 micromolars, if I remember correctly. Yeah, that number is correct. So the overall concentration of oxygen in our ocean is very less, the mean concentration. And in this partially oxygenated ocean, there are some regions where you could develop a complete anoxia. If these regions, if a hydrothermal vent is located in these regions, you could have iron 2 building up here. And wherever well-oxygenated waters would meet with iron-bearing waters, you would have precipitation of iron 3, which is at this dashed line. So iron-bearing waters, which are coming up from a hydrothermal vent, whenever they meet oxygen-bearing waters, you create a chemical deposition front. And at this front, you'd have deposition of iron 3. The latitude depth profile shows the same picture. you see we have a lot of oxygen. Well, comparatively, we have some oxygen at the near the surface, and in the rest of the ocean, there is limited supply of oxygen. And the ocean circulation is such that you could form this patch of oxygen-free region. Iron too can build up in these anoxic regions, and wherever these iron-bearing waters meet the oxygenated water, you would have precipitation of iron 3. The dashed line marks the chemical deposition front in this case. Now we need to explain these results. So if you look at the ocean circulation, because it's an ice-covered ocean, which is being forced with winds only near the equator, it is a lot more sluggish than the present-day ocean. There is an overturning circulation, but it is mostly constrained to the equatorial region or the tropical region. If we focus particularly on these juvenile ocean basins that were formed during the breakup of Rodinia, where a hydrothermal vent is also located, the ocean circulation is quite sluggish. So any oxygen that is produced in this nutrient-deprived ocean is not being circulated well enough. So in these poorly ventilated regions, you could have buildup of iron, and because there's limited supply of oxygen due to the circulation. If we consider the other hydrothermal vent, which we had in the model, what we see is this is located in the well-ventilated part of the ocean. And in this well-ventilated part, you do not see widespread iron deposition, which explains, the ocean circulation is the key factor for why we have banded iron formation in this region of the ocean, but not this. It will be clear on the next slide when I show you the deposition map. So this is the iron 3 deposition map that is obtained during from these simulations for a 12 south to 12 north ocean with a 3% modern phosphate level. So as you can see, the iron deposition is mostly happening in these juvenile ocean basins, which are located near the hydrothermal vent. Interestingly, all but one of the banded iron formations that have been dated to the Sturtian glaciation are found around this region, except for this one. And any iron that is coming out of the hydrothermal vent in the well-ventilated part of the ocean is precipitated at that very grid cell. So you do not have any precipitation of iron away from the hydrothermal vent. The dashed line here marks the minimum concentration that we had estimated from the Sturtian BIFs. We are 1 order of magnitude higher than that minimum concentration. So it is possible for a soft snowball to sustain iron deposition rates which are high enough to precipitate Sturtian BIFs. We don't just see that in one case. Even in a 30 south to 30 north ice-free ocean, you could have widespread deposition of iron. Now, I've been using this adjective again and again to the adjective widespread. What do I mean by that? Let's focus on this part of the ocean. This is the furthest from the hydrothermal vent where you have an iron precipitation rate high enough to deposit BIFs. So the location of this patch, the distance between the location of this patch and the closest hydrothermal source is 3,000 kilometers. To put things in perspective, I think it would be like seeing precipitation of BIFs in New York when your hydrothermal vent is located in close to Florida or Southern California. No, Southern Carolina, right? 3,000 kilometers is a long distance. So to conclude, if your seawater phosphate concentration is between 1 and 10% of modern levels, both the spatial pattern and the magnitude of iron 3 deposition rates tend to agree with what we have found using Sturtian BIFs. A nutrient-deprived glaciated ocean in which the marine ice extends well into the tropics, allows for both the accumulation and mobility of iron 2 in the ocean, which has a very short residence time in an oxygenated condition. All of this precipitation of iron oxides happens at chemical reaction fronts where iron-rich water meets oxygen-bearing waters. And the circulation in the young ocean basins that are formed during the breakup of the supercontinent allows for this area of sluggish circulation to develop. So any oxygen that is produced in the ocean cannot penetrate into these regions, or the rate at which it is circulated is sufficiently small to allow for accumulation and mobility of iron in these regions. A common notion about the precipitation of banded iron formations during the Neoproterozoic has been that you need high concentration of iron throughout the ocean for these BIFs to precipitate, to explain the widespread precipitation of this. Our study shows that you do not need high mean concentrations of iron 2. And that's about it. You can find this paper in Nature Geoscience. This was published recently in April this year. Thank you. Questions?
Kaushal. Questions? Doesn't this support your hypothesis?
I have lots of things to say, but I would dominate, so
No, please go ahead. Anybody.
Well, go ahead, you go first, Ron, then they can take over.
So this is a tourist question, it's supposed to be an expert question. But, so one piece of evidence against a soft snowball is the buildup of all these cap carbonates. So it's kind of a similar physics or geochemistry. Would that also allow you to build up a lot of carbon in the ocean just because you're keeping it isolated? I mean, you basically don't have a lot of mixing just due to the sluggish circulation. Is that a way to get around that?
If I remember correctly, the cap carbonates have been, it is thought that the cap carbonates formed post glaciation, right? So again, none of the assumptions that are presented in this study deter the ocean from having a lot of DIC and alkalinity to build up, which I think is required for precipitation of cap carbonates.
Right, so I guess that's my question. So we know the cap carbonates come after the snowball route.
Yes.
But if you have an open ocean, you can imagine that, you're fluxing all this. So my understanding is that the idea is that volcanoes are continuously putting CO2 into the atmosphere. And if you had a hard snowball, that CO2 cannot get into the ocean, and therefore, if you could eventually break up the ice, then all this CO2 would invade the ocean, and then you get these cap carbonates. So, but it sounds like if you have really weak mixing, you can actually keep the CO2 out of the ocean, even if you have like open ocean in some places.
I mean, that would not be a function of the mixing inside the ocean, but rather a function of how much area of the ocean are you keeping open. If you have a small enough area,
Right.
you could have a limited flux of CO2 exchange. So in the scenarios that I showed here, the snowball that we discussed throughout this talk had an ice-free region of 12 south to 12 north.
Right.
So it is not a lot of area to keep open. I think what you're saying would be a good constraint on how much do you need to open the snowball up for the DIC and alkalinity to increase enough, even in a high CO2 atmosphere, to deter the precipitation of cap carbonates.
So it's true that the extent of the ocean is very narrow, because you have a lot of time, and so.
Yeah, it's 60. The longest snowball was 60 million years.
Right, okay,
Yeah.
but it seems like, if you have something coming in, if you have this flux in at the tropics of the sea, then doesn't it kind of get diffused throughout the rest of the ocean in that time? I mean, is there any, I guess I'm trying to understand why it matters that having a relatively small opening is important to keep the amount of carbonate.
So your initial argument was that if there is a lot of atmosphere and if there's a lot of CO2 in the atmosphere, all of it could rush into the ocean as well. that rushing is determined by how much area that you have for gas exchange to happen.
But
If you-
rushing also depends on how long. I guess I never really, okay, so maybe rushing was not that, was not the best word, but imagine if you have volcanoes that are constantly putting CO2 into the atmosphere. And you're continually taking it out of the atmosphere into the ocean. And it's just getting diffused out into the ocean, then you can start forming carbonates, and so I guess that's the thing I'm wondering about. I mean, so you're basically telling, I think you have a really interesting mechanism for forming banded formations. In spite of the fact that, you have an open ocean, and, some oxygen at the surface. I'm just wondering if like similar physics, allows you to have a large amount of CO2 in the atmosphere and not have it come into the ocean.
Couldn't the cap carbonates also be from like you're saying, if it's after the snowball Earth, you have the ice sheets recede and you have all the conditions that life needs, and you have these huge balloons that are depositing really fast. I mean,
So the thing about the cap carbonate, they're capped because they cap the glacial deposits for very few. Is that they have an unusual carbonized carbon signature.
Mhm.
And so the original explanation for that required having your atmosphere and ocean carbon reservoirs completely distinct from each other until the end. But that's not the only way that you can create cap carbonates. You can also do that by destabilizing methane evaporates in the sea surface, in the sea sediments. As deglaciation progresses, right? Because evaporates are pressure and temperature dependent. So in that case, you don't ever have to worry about keeping atmosphere and ocean carbon reservoirs separate, because the negative signature of the carbon and the methane is supplying the negative aspect to the cap carbon resistance.
Okay.
So it just depends on which hypothesis you prefer.
I mean, I'm not an expert in carbonate geochemistry. Barring that, one of the explanations for cap carbonate is that we had a very warm environment after glaciation, and if you dissolve CO2 in the ocean at that warm of a setting, it just reaches a saturation concentration and then precipitates as cap carbonate. So the only constraint from even that simplistic argument is that you don't have to reach that saturation concentration, and with the limited exchange, air-sea exchange, I think that can be sustained. The shape of the snowball here is merely schematic. If we refine this model sufficiently, I think we can find a scenario in which you could have cyanobacteria sustaining. You could have an ocean which sustains cyanobacteria, but still have a limited enough exchange with the atmosphere to even support the first hypothesis about cap carbon.
Okay, Linda, your turn.
I'm just curious, does the MIT GCM have dynamic sea ice capabilities?
Yes, it does.
Have you tried any experiments using that rather than describing it?
Okay, so this is not sea ice. This is ice shelves.
No, I'm just generally speaking, have you tried these experiments?
No, but there is a reason for that. I think in the early 2000s, John Marshall, he carried out a bunch of simulations using sea ice and an ocean, and the ice thickness that he obtained was 200 meters, and the ice was still freezing. So in MIT GCM, so if you have that thick of an sea ice, it's just wastage of computational resources, because in any case, whatever is the nature of the sea ice, we do not expect light to penetrate, photosynthetically active radiation to penetrate below 200 meters thick block of ice. So to answer your question, I have not tried the MIT GCM's configuration with sea ice, but there are other people who have done it, and they obtain order hundreds of meters of thick sea ice, and they have to shut down the experiment because then they reach numerical cutoff which is there in the model.
The reason I ask is because the term sea glacier was created by Jim Caston, who's an atmospheric chemist. And he came up with that terminology because the original snowball Earth hypothesis that was put forth by Paul Hoffman and Dan Drag suggested that the freezing over the ocean happened to be extremely rapid. So they did not allow for the buildup of ice sheets on land, which is a problem because we had evidence of ice sheets on land. And so they tried to work a way around this by discussing these sea glaciers as a means of producing some of the deformation and shallow marine environments that you can see, which would normally be ascribed to an ice sheet moving off a continent into the ocean. Right? But instead, they had to have sea ice that was essentially going straight along the edge of the continent. Jason Goodman, who did some 1D sea ice modeling for Jim Caston, was getting the kilometer thick sea ice. But he told me that subsequently he was trying to reproduce that effect with CESM, and he could not. So he completely abandoned it because it was simply not possible to generate that much sea ice with CESM. We have also not had the experience of being able to generate that much sea ice with the distribution that ROCKE did.
Okay.
And so that's why I was asking, why you were doing that here.
So the focus of this project was not to look at the exact nature of the ice extent. The goal here was to focus more on the biogeochemical aspect of the snowball Earth debate and to attempt to put some sort of constraints on the meridional extent of ice cover. I mean, scratch that. It is to put out this notion that because we see BIFs, it had to be a hard snowball out of the discussion. My idea was to propose that a soft snowball can also sustain banded iron
And I
formations.
completely agree with that.
Yeah.
Because you have environments in modern day Earth that are not glaciated at all. The Red Sea, for example, where you have anoxic iron-rich bottom of the
Yes.
that would eventually produce something like that in iron formation. So that I have no problem with with that end of it. So that's why. But I was just wondering why the prescribed ice cover.
So the prescribed ice cover is because there doesn't exist a dynamical thick ice model which can account for all of the physics and be implemented in a climate model.
I guess my point is, does it even have to be that thick?
Oh.
So that would be a separate question, which I know you're not addressing.
So then.
So you want it to be thinner? You want the glaciers to be thinner? Sea glaciers.
So I mean, there was no such thing as a sea glacier until the early 2000s with the discussion of snowball.
Right.
So it's just sea ice cover.
Right.
And
So you're saying that they're too thick. You're saying 200 meters or 1,000 meters is too thick, and they might as well, they could be 50 meters and that will be okay.
Well, yes.
Okay, yeah, right. Okay.
A kilometer seems to be a product in Jason Goodman's case of the 1D nature of his model.
Right.
And when he tried to do something that was using a dynamic sea ice model, he just could not achieve those thicknesses. So if you could achieve this with something less than 200 meters of sea ice, what you described here, not it is the thing that I'm curious.
Well, would you see a big difference though? I mean, you basically get some more light into the ocean, right? If it was, say the ice was 20 or 50 meters, some light actually might reach the ocean. Is that what you're saying? Or what would be the difference from your point of view from going from 200 meters to 50 meters? What's the big difference?
Well, for me, it's more a matter of what processes are you simulating and how realistic are you?
Right, but he's fixing one process, which is the sea ice extent, which is probably a good thing to do.
Right,
But the
he's
thickness,
also fixing-
no, but that's what I'm asking. So he's fixing both those things, but what would be the big difference if he changed the thickness? I mean, if you think about it, what could be the difference? in terms of what his experiment is producing.
So are you asking how fast light it's?
Yeah, so the
through
sea ice
the ice?
are, let's say the sea ice is not 200 meters, but it's 50 meters. Would that make a big difference in the results here? I don't think so,
It
would
would
it?
depend on the opacity of the ice. in
Yeah,
that
but-
case.
Right.
And also
How much?
the amount of heat. If you have 200-meter thick ice, you're not gonna have a lot of cracks, presumably like in that thick ice. So
Right, right.
You have some thin ice. You can do that, and then you have, there's the gas exchange happening. Yeah.
But then that works against the
Places-
BIF, that works against the BIFs then, doesn't it?
No, you
No,
don't have to.
Does not have to, but.
So that's why I'm just interested in looking at this without having a constraint that is highly artificial versus something that is perhaps more realistic.
It's possible that the newer sea ice dynamics strategy, like the EVP, LST, viscous strategy might be able to handle more efficiently thicker ice on the other. I think
I have a couple of-
there's an option now in the MIT GCM computer in EVP. But yeah, I'm not sure for 500 meters.
I'm not aware of all of the features of MIT GCM. It's very dynamic to keep track of everything in all the states. That being said, there were a couple of papers by Ellie Zipperman as well, who uses not a 1D, but a 2D model of energy balance. And he obtains anywhere between 600 meters to 1000 meters thick ice. So there's that evidence. Also, the idea for using 1,000-kilometer ice sheet comes from one of my advisors' paper. His name is Yosef Ashkenazi, who considered latitude depth ocean coupled to an ice ocean and sort of ran this setup asynchronously until he found what would be the equilibrium concentration, equilibrium thickness at which the energy balance would hold, meaning that whatever geothermal heating is coming out, go out. And the thickness which came out to be was 1,000 meters. So there is some motivation for why am I using a thick ice sheet. I mean, we use similar models to estimate the thickness of Europa. The surface temperature of Europa can be used to extrapolate what the thickness of the ice is.
Is rather different for a bunch of other reasons. That's okay. I mean, the geochemistry I like, but that's.
Thank you.
I'm totally on board with that.
Any more questions?
Can I make a comment, Mike? It's
What,
Mark.
one online? Sorry, go ahead.
It's Mark Chandler.
Oh, Mark, go ahead.
I just wanted to make a comment that you know, some of it maybe just in the beginning of some of these presentations like this. I think it's a great presentation. It's really interesting. But the whole things like the sea glaciers rub some of us the wrong way, since they were essentially just made up the concepts. And there's really there's no geologic evidence for something like a sea glacier. It's just a hypothetical. And so, you know, I was just on snowballearth.org, and you know, which comes out of the Harvard group, and you know, they present so many things like they're just a fact. And some of us who've been in this game for 30 years just get really frustrated with how some of these things get into the lexicon, which are really just made up. And there's a lot of it made up by modelers who took on the really cool concept of modeling the snowball Earth. So I don't know what exactly Lindo's point was there, but I think that the truth is we don't need to go to some of these extreme, you know, explanations. That the idea is that if you can produce this amount of ice cover at a realistically reasonable thickness, you know, not 1 meter, not 10 meters, but 50 or 200 or whatever. We don't need some of these, like the sea ice glacier mechanism really was there to try to say we need some mechanism to form a hard snowball. And most GCMs with reasonable boundary conditions were coming up with ice-free tropical oceans. And so some concept of some flowing sea glacier, again, there's no geologic evidence for anything like a sea glacier any time in geologic history. We don't even simulate land glaciers well, right? Which we know a lot more about them than some made up sea glacier. Anyway, I would just caution and say, I don't think your hypothesis here, your paper needs anything like any discussion other than if you can form an ice covered region similar to what your images that you're showing there. And GCMs have formed that type of result before using dynamic ocean models. So, it may be the narrowing of the ice-free region that you have there may be a little difficult to get, with sort of modern dynamic coupled ocean models, and I wouldn't put any stock in 1D or 2D models when it comes to ice thickness, sea ice thickness, because the horizontal heat transport in the oceans and in the atmospheres is so parameterized in those models that I just don't think that's the kind of model you would use to support any type of sea ice thickness. But I think you can probably get your result with models like the one that, are, being developed at GIS or maybe others. So.
Mark, thank you for the input. I would possibly refrain from using the word sea glaciers again, because the whole point was to impose a prescribed coverage of ice to simulate what a soft snowball may have looked like. I agree that a lot of terminology which creeps into the lexicon, is that the word? Into the lexicon may not sit well with the geochemists and geobiologists and physical oceanographers and people who have spent lifetimes working on this problem. So I'll keep that in mind. That being said, the result that you see on your screen, on the right-hand side of the screen, panel B, is for a 30 south to 30 north ocean. And as soon as we have a biogeochemical package at GIS, which is suitable for doing Neoproterozoic snowball earth modeling, we could try this out using any model. The reason for using this particular model is because that was the model I had my hands on. I had to code it in. But
Absolutely.
The goal is.
Can I just, while you're there and while Linda's still in the room, can I ask Linda, there's been a couple of proposals between you and Natasha. Would those models be able to do this? I'm sorry, Natasha has our ocean biome model.
Okay.
Maybe I'd like to hear the discussion between the two of you. So,
I don't know if those modifications would lead into the work that Kaushal is doing here.
Okay.
Because the proposal that I had with her was more about updating the ocean biogeochem portion of the model for non-modern Earth organisms.
I see. Okay.
Not so much the chemical interactions in the ocean.
All right. I'll shut up.
Okay.
I have a somewhat naive question. So you mentioned the 2 snowball Earth events.
Yes.
And are these associated with any sort of mass extinctions or anything like that in Earth history? Do you know?
That would require us to precisely date the mass extinction. I don't think these 2 snowballs are associated with any, but this. Now I'm afraid of using another terminology. This explosion in complex life forms, that seems to be dated around 540 million years. And I think one of the popular theses is that the snowball Earth, the latter snowball Earth event, the one which is closer to the modern time, may have triggered, but this is just things that people have put in discussions, which there's no evidence that I'm aware of to show that the snowball Earth led to an explosion in complex life.
Yeah, no, I've heard that sort of passed around a little bit too, but that's just,
I refrain from diving into these tangents because there's a lot of uncertainty, both from a geochemical standpoint and from a modeling standpoint regarding these events itself. So drawing any parallels to extinction or life bloom events, I'm not aware of any.
I mean, 'cause
Grounded ones.
it seems to me, and this is again completely naive, that if you did have a hard snowball, that there would be some sort of bottleneck there in the fossil record, right? Or,
We
you
would
know,
expect that.
Yeah. maybe, and
Why is that expected?
you don't have, I mean,
Not very
you don't
productive.
have any surface life, or at least it's not super conducive to surface life, anything photosynthetic.
I wouldn't go that far because even in a hard snowball state, if you have these lakes above ice, they could sustain photosynthetic activity.
Yeah, but those would be reasonably extreme environments, right? And so you would have some sort of bottlenecking in the it's certainly in the microbial record. I don't know that we see that. I'm not a microbial whatever ecologist, so I wouldn't know, but yeah, it seems logical to me that we would have to have some sort of climate conditions, at least spatially on Earth, relatively consistent throughout. Yeah,
I'm not in a
Yeah,
situation to answer
maybe,
this
yeah,
question. I
maybe,
think a geobiologist might be better equipped to
Mhm.
answer this question. I'm sorry about this.
yeah.
Yeah.
Any other questions?
Yeah, any other questions? Okay. All right, well, thank you again, Kausha. It was
Thank you, everyone.
fantastic.